So welcome to week 5. You guys have survived, and so far the Rona hasn't killed me yet, but it's sure trying. I don't actually think it's Rona, but there are other viruses, as it turns out. So one of the things that I wanted to hit on this week is, having now gotten a sense of what forces and angles do and what we might use them for design principles in how these engineering processes work, is something that we think of often as being brand new to us, something that we did, something that we developed and generated and we created. Turns out if we read, what has been is what will be, and what has been done is what will be done, and there is nothing new under the sun. Is there such a thing of which it's said, see, this is new, it has already been in the ages before us? This seems like just a nonsensical statement on the surface to a lot of people until you actually really understand what it's trying to tell you. So on the right is a recently published paper or a figure from this recently published paper where one of the most complex mechanical mechanisms in all of nature has been found. This is a 10-bar linkage in the jaw of a fish so that it can actually extend its jaw out and bring its mouth to where the food is. So whereas a lot of other fish don't have nearly the same kind of complicated jaw, this is an example of one that has a 10-bar mechanism. So most mechanical engineers will tell you something like a 6-bar mechanism is kind of the upper limit for what you would want to design for real systems, and that's for many, many reasons. The main reason for this is it's very hard to constrain and control something like a 10-bar mechanism because it's almost over-constrained in a lot of ways. One of the other things that is very important to understand is if you change on something like a 10-bar mechanism, the direction that you're applying the force, think back to the pulleys lab, what do you guys think actually happens as far as the packaging of the fish? You have to change the size of all of the musculature, and now you have to completely redesign the whole rest of the fish because it doesn't fit with the packaging. So there's a bunch of different examples of these complicated fish jaw mechanisms as just a simple example. There's actually zillions of these examples in nature. There's a bunch of ones that have been highlighted here in this picture, showing kind of the skeletal overview of what the actual mechanics are of these fish jaws, and it's really just exceedingly impressive. Lots of different kinds of designs to do lots of different things for these fish, and all fit specifically into their packaging exactly as they are, and you can't change them without changing literally the entire fish and doing a complete redesign. So it's pretty cool. So since we've got just about all of us now, we've got a bunch of things going on today. We're looking at sinusoids. I was going to do a quick demo in Simulink, but that's kind of getting beyond the scope of what we're trying to do in the class. The theory here is when you combine two very different kind of waveforms, what are called sinusoids, these sine waves collide and do some very different sorts of things. So they add and subtract from each other to get a very different kind of combined signal out the other end. So what we're going to be doing is actually going to be looking at this, and we're going to see, okay, based on a simplified Tinkercad model, we're going to look at the new updated prompt, and we're going to look at this Tinkercad model, and we're going to start making some adjustments on this Oscilloscope so that we can actually read some things. Now, had we been physically in class this week, it would have been a little bit easier because you guys would be able to see on the real Oscilloscope how this stuff works. For the purposes of what we're trying to teach you, this will show a demonstration just fine. So one of the first things I'm going to have you guys do is I'm going to have you guys take this idea and put it together. So grab a quick screenshot. What you're going to want to do is apply this in Tinkercad. So I'm going to switch over here to Tinkercad, and I already have this as an example pre-built. What we're going to do is start manipulating, changing the resistors that are included and all kinds of things like that. So we've got a couple more of you, I think, logged in. We have just about everybody now. So this is what we're aiming for in Tinkercad. I'm going to switch over to that. Again, sorry for the extra confusion today, but this is just part of the fun and excitement of now when we get sick. So you'll see a new document that's got a couple revisions to it. There are some definitions here that have been added to help clarify a couple points. So we're going to talk kind of as we work through this. I'm going to have you guys download this from this week's announcement. We're going to work through this and build some of these different kinds of circuits, because all of these components are in Tinkercad, and we need to know what some of these values are. So we're going to walk through a little bit of that in order to make some of this stuff actually make sense. So we're going to leave that where it lies. Yeah, so Tinkercad, it'll be a whole lot easier since you can actually see what's going on here. So you're going to want to switch in Tinkercad over to all components, and we're going to pull out a few things for use today. One of them is going to be we're going to find the Oscilloscope. So down here we're going to need a breadboard. We're going to need a power supply, actually a function generator rather than a power supply, and an Oscilloscope. So these are two instrument types that we're going to be using for today. So the function generator, what this is going to do is we're going to set our parameters to what we see for different tests that we're going to be running based on the handout. So again, that's going to be the handout for that's attached to this week's announcement. And what we're going to be working with is understanding the fundamental things that are being talked about here on the handout. So amplitude, frequency, period, phase, time shift, these are some of the key important things here. So the amplitude is the size of the wave. The frequency is how close together they are. The period has to do with the time it takes to complete a cycle. And then the phase is the horizontal shift. So this is something that becomes really important, especially for electrical engineering. So the model that I have up on Tinkercad, you guys aren't going to find a link to it. What you're going to do instead is you're going to have to build it from all components. So what you're doing is you're looking at putting on the Oscilloscope and the function generator from all components. So I'll give you guys a couple seconds to get those set up. This circuit that I have up is one of the first examples that's in the document. So function generator, a resistor, and an Oscilloscope. So this is one of the first ones that we're working on, and this is where that comes from, is it actually comes from the document itself. So there's going to be a few different kinds of circuits that we're going to be measuring, and we'll kind of walk through some examples of these. So hopefully everybody's getting there. All right, what we're going to set some of our settings to is we're going to start with making sure that we set our resistance value. So this, for the first one, it calls out a 50 ohm resistor. So that's going to change our color band. And assuming I don't have to load the interface again, I'm going to refresh this interface. Every once in a while it will not accept a change. we've had all manners and types of technical issues earlier today, so I'm expecting nothing different from Tinkercad. So 50 ohm resistance, there we go. So 50 ohm resistance. We're going to set our parameters. So this is based on this figure 5.2 again. So we're using a 50 ohm resistor, and we're going to work on what we need to get from table 5.1. So that's this one. Table 5.1 we're trying to fill in. So there's a couple new terms, and we'll talk about what those are. But first, knowing what settings we're actually going to be using. So using an Oscilloscope, what we're going to do is we're going to make measurements at, or we're going to use, for our function generator here, we're going to use our 2652.5 hertz for our function generator. So it's a little bit of an unusual value, but again, a lot of times what you're entering into a function generator will be. So this is 2652.5. The amplitude, we're going to set this based on this amplitude. We can adjust. So based on what's in table 5.1, what we're going to do here is we're going to say 2.5 and then we're going to look first at what it does at kind of this frequency. We'll just do 1 volt. 1 volt. I'm going to do a 0 DC offset. We'll talk about some of what these are. Pardon me. We're going to talk about what these are. We're going to leave it as a sine function for now. We're going to set it just at this frequency. Then we're going to make adjustments to the timing on this. So this is something that will make a little bit more sense as we go to run it. So we want to run positive into the positive rail, negative across on the negative rail, and we're connecting this just like it looks like in that figure 5.2 that is. So here, when we start our simulation, we're going to get this because you're going to set your time divisions down to about 100 microseconds, which is the mu s here. So 100 microseconds, if you start off with the default, it's something like something crazy like 1,000 milliseconds. What it will do is it will change. Let me restart this to get it to replot. Okay, so we should have a clear display. The problem is that one's too long a time scale. So you might see something like 10. It will update automatically, but this is a thing that would make a lot more sense in person. Basically what these are doing is we're setting the time constants to be able to move things up and down. So yeah, I'll give you guys a couple seconds to kind of catch up a little bit. These are all new tools and all new terms that we're learning, so we'll kind of walk through what this looks like together.
Is that a 50 ohm resistor too?
Yes, this is a 50 ohm resistor. So 50 ohm resistor, that's the first one that we have as our reference point. What we're trying to do just initially is get you guys to get a sense of playing around with this a little bit and seeing what's involved. The function generator and the Oscilloscope are some of the only things that you can move and change while the circuits are running. I think you can maybe do that with the power supply, but I'm not certain. So in Tinkercad, these are some of the only ones you can change. To get a sense of what these look like, we can also generate square waves as well as triangular waves. We're not going to get too far into what the different applications of those are, except to say that the square wave is more of a digital signal, so on and then off. Analog is more like what most natural systems behave like. So the world is very analog. We can emulate very small digital steps in order to behave more analog-like, but most of the world actually behaves in an analog fashion rather than a digital one. So we can also use the knobs and things to change these. It's easiest to change values up here. So if we were to change the frequency, go back to something like 1,000 hertz, the frequency is how many of these instances happen per second. So that's meaning what we're going to be doing, the time division on the Oscilloscope, that changes based on the frequency. So that's part of what we're looking at now. So right now I've got it set on 100 microseconds, which is the µs. 100 microseconds. So what this is doing is this is trying to get you to see some of the relationship between, if I change the frequency, I change what's going to come up on the Oscilloscope, and sometimes I have to adjust what's on the, I have to adjust the time constant in order to observe the changes. So it's really cool to see this in person. It's really unfortunate that I had to get sick and create all kinds of issues. So it happens. It's unfortunate. Another thing to look at real quick as we kind of play around and change a couple of the values to get a sense of what's happening here is if we make a change to this and then we say, okay, now I'm going to apply something like a DC offset, and I'm going to say let's do a 2-volt DC offset. What this will do is it'll rescale my y-axis. We don't really have y-axis control on this. We really only have time control. In a real one, you have voltage scale control as well as time axis control. So this is a little bit limited and simplified to make things a little bit easier. So here, if we did a 4-volt amplitude, we have plus or minus 2 volts from a 2-volt baseline, and that's what you see. Each of these grid lines is representative of, on the horizontal are Y delineations, so these are all voltage, and then up and down the vertical is all number of thousands of microseconds. So this is now on a 10-volt scale. If we reduce this and do a DC offset of 1, we can now see the center line is at plus 1 volt. Yes, I am recording this, so they won't hear any of your questions directly, but they'll hear answers to questions. So I'm trying to record this so that everybody has a chance to go back over this. This is very new and different kind of stuff, but it's one of the only ways to get you guys to actually be hands-on with sinusoids in a way that doesn't require really outlandishly expensive equipment and things like that. So this is what we're doing. So you'll have to bear with my voice. Hopefully it will last for the whole time. Jury's out on that. All right, at a 0 DC offset, we come back down to the center line and we can change our amplitude. So what that's doing is just shifting our graph up and down with respect to the baseline voltage. That's pretty much what it is. So we'll also take a look at what happens when we take a couple of these other a couple of these other values and make some changes to them. We change the amplitude. That one's fairly self-explanatory. You can see sort of live as it changes. The amplitude is by how much it goes up and down. And this is where we get a sense of what's our actual what our input looks like, and that's going to change based on our output. So there's ways to estimate using this what, for instance, our peak-to-peak voltage is, and the easiest way to do that is by changing our time division and seeing what happens. So if we did 10 microseconds, for instance, we would do so this is like 100 microseconds. Let's see. So this we could probably get away with doing 50 microseconds. There we go. That'll be a little bit easier. So on this scale, we have each of these units should be 50 microseconds, meaning the whole scale, all 10 units. Because note there are 5 small divisions within each of these. So 1, 2, 3, 4, 5. Each of those is a block representing one of this scale, 50 microseconds. So how to read this would be from 0, this would be 50, 100, 150, 200, 250. That's half of the 500 total on the whole scale. So if we were to zoom in here, we would see this is actually showing you what the physical scale is. Same thing for the Y. This physical scale right now is 2 volts. We have plus or minus 1 volt, because that's half of this scale. We have plus or minus 1 volt, giving us an amplitude from top to bottom of 2 volts. So that's what we have here. So 1 volt up, positive, 1 volt down, negative, gives us a total range, a total amplitude of 2 volts in the analog sense. So when we go to 2, this increases, and so we see the scale now changes to 4 volts, and so the scale is there trying to help you. So what you can do is, even at something like 1 volt, you can measure the volt sort of peak to peak, which is this sort of whole range from one peak to the other, is this amplitude times 2 is what that should be. So that's the VPP that you guys haven't seen before. VPP is going to be very, very useful for a lot of the things that we're working on. Answering a question real quick. The range as far as the frequency. So again, 500 microseconds, we would go 1, 2, 3, 4 steps. So this peak to peak time between these, so the ability to go from one point on the sinusoid all the way to that same point on another wave, is going to be 1, 2, 3, 4 divisions. And so 4 times 50, which is our actual division here, is a period of about 200 microseconds. So 200 microseconds tells us something about the frequency, and this is 5,000 hertz, meaning 5,000 cycles per second. So this is also a thing that will kind of help to frame the discussion that's going to be happening around this process. So one of the things we want to look at is this voltage peak to peak. We want to learn about the frequency, and then the T the time in seconds. So this is described up here by what we're learning from these equations. So the frequency has to do with the time, and the time is this length here. So the amplitude again is the height of the wave from zero. So the amplitude is both in the positive and the negative sense. The time is from that starting point to the same point on another wave, and the frequency is related to 1 divided by that time. So everyone should double check that I'm not making things up real quick and divide 1 by 200 and see what you get as a number, and just see what that looks like. The angular frequency is another thing that we can learn a little bit about, and that has to do with being 2 pi divided by that time. So there's also a time shift that can occur. So depending on what the circuitry is doing, this one is not really doing any time shifting of the curve, but we're going to see some of that later in some of the examples. So there's a couple other terms. So yeah, the voltage peak to peak is one of them, one of the new terms that you're going to come across. We're also looking at something called capacitance and inductance. So we'll come across these principles later on. Capacitance is the ability to store up and then discharge an electrical charge, and it's depending on the surface area of the thing doing the storing. So yeah, that's something that we'll learn a little bit more about and more significant information about later on. Inductance is running through a coil of wire that changes magnetic properties in the wire because of that current flowing, having to do with the relationship between basically the flow of electrons and the magnetic field, which is why electrical fields and magnetic fields are often coupled. They have a lot of behaviors that are complicated as a result of those. So we're going to look at a couple things here, and what we're going to do is have you guys kind of start playing around with this, seeing if you can get the first couple measurements on this table. So the 5.1 table. We're going to set the frequency of the function generator to 1000 hertz. We're going to set the voltage to 2.5, and then we're going to try and determine some of these factors given what our values are up above, right? So you'll see a couple oddities here, like the time in seconds and the time in seconds again, and it's saying this is measured, this is calculated. So the measured is going to be what you're pulling off of this oscilloscope using the counting method that I was just showing you. The frequency is going to be calculated again from the timing. The voltage peak to peak is going to be showing you again from the peak of one to the peak of the other. And then we're going to be looking at when we change some of these circuits, we'll come back again and start adding in a couple of these other components. And so we'll look at a different method of connecting them. We'll try and make them look as much exactly like this as possible. And so we'll talk about how to do this on the breadboard and make it simple, because this looks scary since it's 4 different components, but it's not actually as bad as it really looks. So what we're going to do is this time. So the time shift is really what they're looking for at the very, very end there of 5.1. So they don't have it listed that way, but they should, the time shift there. So then we're going to look at VS, VC, and VL. So again, just a couple kind of fundamental clarifications here. The L is used for inductance, C is used for capacitance, and so looking at the VC where the capacitor is, and then VS is the signal, so the signal that's actually being sent through this particular circuit. So we'll talk a little bit more about the mechanics of that. So I'll have to kind of record this in a few pieces as you guys work on it, and then kind of blend it all back together at the end and hope that it makes some sort of overall sense. So I'm going to have you guys do this first part where you're changing a couple of these factors. You should be able to fill in table 5.1. Then we're going to take a look at figure 5.3. I think so 5.3 is included here, but we're going to come back in a little bit and show you how to make 5.3 on the actual breadboard. So I'll let you guys work a little bit on this first part, and I'll kind of pause recording here and then see where some of the questions are, because I'm sure there's going to be quite a few. So here's the prep for the second step. This is trying to get after what we're doing here. What we're doing here for this particular figure. So working with 5.3. So we're going to set our component values, and I'm going to show you a way to set this up in a way that should make a little bit more sense. So the first one is going to be looking at this side versus the capacitive side. So then we'll look at the inductive side, and so we'll move the probe around and show you what that looks like. So the function generator is the FG. Function generator should be coming in here and here. So instead of making things far more complicated than they need to be, I'm going to kind of walk through why I have this arranged the way that I do. So without moving the function generator, I just set up another quick breadboard here, and this is probably about the simplest way to show how to do this. So again, we have our same 50 ohm resistors. So those two 50 ohm resistors are going to be vertically. So instead of doing it in Tinkercad to make a truly diamond shape pattern, which you could do on the real breadboard easily, Tinkercad we'd have to make wires and do other things to make it work cleanly. So we're going to treat it like it has a straight piece of wire in between these two and a straight piece of wire. In this case, these guys are just connected together directly. So each of these values has a range. So 1.2 microfarads is what our capacitor is. So the capacitor, we should be able to see, there we go, 1.2 microfarads. And then these are, this is 3, I seem to recall they're in millihenries for these, for inductance. So a whole bunch of historic reasons why that is. The mechanics of that aren't really important for the sake of this class. Just understand that there is a unit associated with that. You'll learn more of the history stuff later. So we have our inductor. So again, that's under all components. We have our inductor, we have our resistors, we have our capacitors. So these are the little M&M shaped things on circuit boards that you guys have probably seen before, haven't really appreciated. They do have a function. They store and release charge rapidly. So for this one, the way that we have this hooked up, we're connected to one side for the oscilloscope. We're connected to one side of the capacitor. So this is looking at, just like in our diagram here, our channel 1 red. This is going to our oscilloscope. Our channel 1 black is going to our channel 1 black, and our function generator FG black are all going to the same place. So right now I have them crossing. They could be in the same row since these two are tied together with a wire. That would also be acceptable. The idea is just to make sure that they're electrically connected at before basically these resistors. So it's important to have them located correctly. So one goes from the resistor pairing here over to the function generator, one goes over to our oscilloscope. So pretty straightforward there. Then what we're going to do in a little bit is switch it over to measure on this side. So basically what that's going to look like is just relocating this wire from this side over to this side and making things a little bit easier like that. So this is the two different measurements that we're actually going to be making on this. And so these two are still connected. We still have our function generator. So this one, we're still running the function generator on the same point where the capacitor and the inductor are connected. So that's here. So we're still running the function generator in the same place. And then all of this using a frequency of 2652 and a half. So this is our frequency for the function generator. So frequency of the function generator. What we will now see when we go to run this, as you guys are kind of getting caught up a little bit here, this is not necessarily time shifted, but we're going to get a little different kind of waveform. The measurement for the inductor is pulled off of our sheet here, our spec sheet. So 1.2 microfarads for the capacitor, 3 millihenries for the inductor. So make sure it's mH, not mu or N. Those two are very different scales, so make sure that it's millihenries that's being used there. And we're still using our 50 ohm resistors. So then what we're going to do is start coming down here and filling in table 5.2. So the voltage for this supply, this signal, is 2.5, and what we want to look at is the capacitive voltage. So this is the first one. We're going to measure VC. In this case I'm actually measuring VL, so I'm going to move this around and do VC. So this will measure our VC. So this is the first measurement we need. And what we're going to see is we're going to see a little bit of a difference here. So note the scale. The scale is going to automatically change on the Y. So you can't just assume it's going to be the same thing. So the scale is going to be here. We've got 2 volts total range. So what this is doing is we're going to estimate how far up this goes, because it is 1, 2, 3, 4, 5, 6, 7, 8, 9, and then we have sort of 2 quarters. We could almost estimate this as a half step. So this is where you guys are going to have to get a little bit creative, unless you want to apply an ammeter to be sure. So I'll show you how to use that just to double check the measurements, since we're not looking on the actual live oscope. That'll make a little slight simplification of what we're trying to do here. So these divisions, so 2 divided by 10 is 0.2 or 20 millivolts. So each step being 20 millivolts, this would be 20, 40, 60, 80, 100, 120, 140, 160. So we have another either couple of quarters or halves, depending on how you want to score each one of these results. And so on a 2 volt scale, this is a sweep of really about half shy on either side, which means about 0.1 on either side, 0.2 subtracted from 2 volts. Somebody that's quick at math, tell me what that voltage peak to peak would be. That peak to peak voltage should be about 1.8 or somewhere in that ballpark, even though our input voltage is 2.5, right? So our input voltage would be 2.5. Our our peak-to-peak voltage now. So this would be a peak-to-peak voltage of 2.5. So if our signal was something like 2.5, then this would be half of that value. So 1.8 divided by 2 would be about 0.9. That's the value that we would see here. So what are some of the initial questions that you guys have on that? Is that making any sense at all? There is a method to the madness. There's always a method to the madness. It's just a matter of whether or not you guys can discern what that method is. You guys will have to remember to unmute so that I can hear you ask the questions, though. Or you'll have to type them up in chat, because I've got both up and I'm watching. This is where we'd make our second measurement. So we would see here a slightly different kind of result. In this case, that's looking a little closer in scale to what our other measurement was, but it's still less than what we would expect to see here from our supply. So we're going to finish filling out that table. Then we're going to look and see what other questions we're trying to answer here. So we've already done the movement, and we're measuring the peak-to-peak voltage. So they also want to make measurements using that same circuit across both of the resistors. So the function generator, we don't have a second channel for the oscilloscope, so we'll have to pretend real hard for that part. So the function generator, red lead and black lead are going to stay in the same spot. Channel 1 is going to stay in the same spot, channel 1 black. What we're going to do is move red around, and we're going to see what's happening with each of these. So this is similar to what we're measuring, but we're trying to measure on this side of the inductor. So it looks real similar, but we're trying to look at some slightly different information. So just for kicks and giggles, what we're going to do is take a look at what these two are. In a 2-channel real live system, you would be able to see a little bit of the timing differences of these, but I don't think we can get a second signal simulated, so that'll create a little bit of confusion. But we're gonna develop a couple more things for table 5.3. We're going to look at both, or we're going to try and see if we can get this information out using Tinkercad. So I don't know 100% if this part will work, because this falls under the category of testing before we have time. I don't know that it will show up on the same one. So let me see if it will. So if I were to bring a second signal wire, I'm just going to see if it'll give me two curves at one time. It may or may not. So let me see what it does, and then I'll know for sure. Yeah, so it does actually give you the composite signal. So this is part of what we're trying to get you guys to see. Let me see if I can help you suss out what that's doing in a way that makes some kind of sense. We might be able to get away with the second oscope. And I need to reload the interface, it looks like, because I can't get it to actually remove components now. Far be it from us to ever encounter Tinkercad problems, but this is also how we do live troubleshooting of what these work like. So the two overlaid signals are part of what we're trying to see, but this doesn't give us sort of an elegant means of actually understanding what's happening. So I'm going to bring in a second oscope just for this purpose and see if I can get it to show us any time distinctions. So I'll change this guy to red. Alright, this might give us the two signals with some differences. I'll have to see if it'll cooperate and give us the two different timings. No, it won't. So what there should be is there should be a difference in the timing, so we should actually be able to see the phase shift. I just don't know that we're going to be able to pull that data cleanly out of this method, but this is what we're going to have to work with, so we'll do that. All right, this, I'm going to make adjustments on the time scale here. And see if we can get this to be a little bit more clear as to what's going on. The resistors are 50 ohm. So what we have is we have a timing shift that's happening, and this is what we're trying to get you guys to see, but it's a little bit difficult to do. So it would be nice to drop this frequency down so that we could see it a little bit more clearly. The scales are basically interfering, so what you have is current kind of running around this loop doing different things. What you see in the waveforms is two superimposed waveforms, and this is what we're trying to get you guys to see and understand. It's a little hard to grasp why exactly you need to know what this is, but this is trying to introduce you to the idea that you can superimpose waveforms on top of each other. So you have what you can clearly see is an overall sort of larger wave, and then the smaller wave is following that overall wave pattern. So let me do a quick annotation, and hopefully this will get picked up reasonably. So what we've got is, make sure it's, yeah, it should be clear enough. So what we have is an overall waveform, and on that wave is riding the high frequency wave. And when you combine those two together, what you get is this kind of behavior, because you'll actually see it line up where you have something like a wave like this, you can see both of them very clearly, but what you have is shifting in time, and that has to do with the fact that this is has an inductive resistance and a capacitive effective impedance, which is a thing you guys will learn a lot more about in later circuits classes. Think of a lot of you, for instance, that are using headphones right now, and those headphones have a series of superimposed signals like this waveform all at the same time. So it looks like a jumbled mess, but it's actually just a series of waveforms superimposed on top of each other, because there's typically only one little tiny speaker that's doing the vibration and translating that signal into your ears. So this is one of the things that's helpful to understand. We have to superimpose those kinds of waveforms in order to do things like actually make music and things that are recognizable as music. So this is what we have going on for the superimposed waveforms. And this is why I wanted to get a couple of these things kind of covered with you guys. Now, because of the way that we're doing this in Tinkercad and not doing the live measurement, it's going to be really hard to look at what that time shift is, because really the only way to get to that is to understand what the phase is, and then look at the angular frequency. So you can calculate the angular frequency either from the frequency or from the time, and then you can get after kind of what the time shift is supposed to be. So you're going to have to kind of estimate this a little bit based on what information you have available. So you know what the value for 2 pi is, you know what the value for the frequency is, and basically the function that we're getting out is you're seeing this phase shift component being added in. So this is what changes where that starting point is. There really isn't a way to change the simulator time or slow it down that I'm aware of. The only thing we might be able to do is to drop this frequency a little bit. So if we were to drop the frequency, we might be able to see a little bit more of a value, but because the impedance is a function of the frequency, it's not going to give us the same values that we need. So because of their tuning together, I'm afraid there's not going to be an easy, simple way. I can cut this in half, drop it down a little bit more. What you might have to do is you might have to take a couple screenshots and kind of make an estimate. So it seems like with each, there's like an average shift in time. So if you pick a certain point on one wave, kind of track it as it goes across, and then just take an estimate for what that time shift actually is. So in real time, how far does that signal move? So how many times does that same point on the wave scale all the way across the screen? That's going to be about the only way to reasonably estimate it. So it's going to be a little bit difficult for you guys, but that's going to be probably about the only way to easily do this without actually being able to lay hands on the real instrument. So you can still get information about the radians based on what that time is. So you're going to calculate both radians and degrees from that time shift using this formula. But you're going to have to estimate that time shift for how far is that moving the period. So it's specific to this frequency for these particular values, and you'll learn a lot more of the complicated math behind that later, like I said, in some of the double E courses. So we're not going to try and teach you all those things now. It's just to try and introduce this topic that we are able to use some of these things. So that'll be something that I think will help you guys with some of the functions. There are a couple other things that you guys would have seen on the board today. So we'll talk about one of those here. Let me pull it up for you. And that will make we've really covered most of it, but I'll bring this up. This is what you would have seen on the board today to show as an example. So the folks that are watching this later will hopefully be able to make some sense of what's actually there on the board. So the breadboard circuit, this is the translation from this figure 5.3 over to the breadboard circuit. So we're trying to figure out what is the overall time. If the amplitude is something like 5 volts in total, so 5 volts peak to peak is the 2.5 that we're using. Y is the same as 2 pi times frequency times that time shift initially, and that's what we're trying to look at for each of the cases. So we can solve for what the time shift might be for each side. So when we're doing this measurement individually, we can take a look at this. So that's the phenomena that we're trying to understand. So if we just look at the one value, we can figure out what the time shift ought to be. And if we run 2 oscopes, they should have a different time basis, but because of how Tinkercad works, we're a little limited in what we can do in the simulated environment. So the real one would show you how far that wave was shifting in time. You can also speed up and slow down the display of the data on a real oscope, which is kind of needed to be able to take this particular measurement. So that's one of the things that I want you guys to just kind of consider a little bit as you're going through this process. So go ahead and grab a quick screenshot of this for use in your calculations. And that pretty well covers the actual content for today. So the rest of this is troubleshooting in terms of how to calculate and estimate what that value for t is, so you can kind of rearrange that equation in order to get the information. So being able to plot this time versus y, that's what our oscope is trying to do for us. We're not trying to extract the data and then plot that in Excel or anything like that, but we are trying to take a look at what should be the time shift value based on what we're seeing from the 2 different sides. So that's actually a pretty good question on this, is to pay attention to the fact that we're looking at peak to peak volts, which is 5, because our input is 2.5. So the peak to peak is 5. And then the total scale being 2 volts, this is about halfway from the top and the bottom. And then we've got 0.1 volts from the top, 0.1 volts from the bottom, gives us, since we have a 0 offset, about a 1.8 volt peak to peak, and that's what we're looking for here. So you do the same thing for the inductive side when you move that over, and then go through the last part, kind of estimating what that time shift is, because it's a little bit hard seeing as it's continually shifting everything from frame to frame. It would be nice to be able to compare them, because you could, if you were doing frame capture, you could actually get a literal time shift in seconds, but it's an annoying process to kind of walk through that. We'll start with a new script. It's called an M file. This is the thing that you develop a lot of stuff in. So helpful to always have some kind of comment that details some information about this. So this would be whatever this is, lab 5, and then your name, something like that. Then you're going to do a couple things out of just habit and good housekeeping. We're going to do clear first, then we're going to do CLC. So the clear wipes out the workspace variables and makes things nice and tidy. The CLC is a little bit is just the command window down here to tidy things up. So 2 different tidying steps at the beginning of just about every program. You guys are getting to learn a little bit about ESG. I guess it's 111 now, ahead of time. So spoiler alerts ahead. We're going to go ahead and do a figure, and then you can leave it empty for the most part. This will just generate a figure that we're going to do our plotting in. So we're going to do plot, and then we're going to plot the function, but before we do that, we actually have to calculate the function. So we'll go super duper confusing and use the same kind of variables that they're using here. So in our variables, we have VC, VL, and VS. So VC and VL, assuming we get variables for this, we're going to generate a time array and do a couple of other things. So I'm going to go super confusing for that name. I'm going to call it T for time. I'm going to generate an array in, let's see, I'll do 0.1 time steps. So 0 to time step of 0.1 to a range of, I don't know, 10 or something like that. Give me a reasonable number of data points. We're going to go ahead and do a name to give this something sort of proper, and we'll call this I'm going to do all 3 on the same plot, just because I'm being I think that's going to make the most sense. So we're going to do all 3. So this will just be voltage versus time. I'm not going to go into X and Y labels and other things. We want to suppress this output with semicolon, because don't ask questions you don't want the answer to. Always suppress the output unless you actually want it. So generating the calculation from this, you'll recall from our formula up here, same thing that we were talking about. So our value x of t, in this case y of t, or v of t, is this amplitude times the sine of omega t plus the phase shift. So we're going to plot a few different things all at the same time, and I'll show you how to do it kind of cleanly in one single command because reasons. So a sine is going to be, or amplitude is going to be 2.5 times, and this is going to be y, or I'll even go v of the first one is v, let's do vc. So we'll do, we'll do vs as the first one. Vs equals, we'll do vc and a vt equals, and then a vt equals, let's press our output, so 2.5 times the sine. So sine is already recognized, and it recognizes, hey, we have a variable sine of t. So we have to remember for each of the different cases, I'm just going to use some examples. I still want you guys to go through the exercise of estimating what that time shift looks like. So we're going to do omega times t. So omega is 2 times pi times, and so this is recognized variable. Pi is a recognized variable. Normally, if something is thought of as a variable and it's undefined, it'll throw error codes, but pi it understands because MATLAB is reasonably smart software. Pi times t times the frequency. So the frequency for most of these trials was 2652 and a half. 2652 and a half times t. So all of that gobbledygook plus the phase shift. So our source has no phase shift. But what changes, somebody that's really paying attention and hasn't fallen asleep yet, what changes with regard to VC and VT? Anyone know? Does our 2.5 stay the same? What's our amplitude? What's the amplitude of our signal at those 2 points? What's in our table? 1.8. So this times the sine of, again, 2 pi times our frequency. Now in this case, what we want to verify is what is our output frequency. So when we're checking this, we want to look at from a point on the wave to the same point on another wave, one complete cycle. This is 1, 2, 3, 4 divisions, just about. So 4 divisions. The voltage source is we can use 5 for this since we're doing peak to peak, so that we're consistent. So the 5 volts peak to peak, since this is AC type signal for voltage rather than DC, this is going to be the same kind of thing, and we'll have to eliminate that second set of suppression because it'll get confused. So this, we want to verify what our frequency looks like. So the frequency, this is for really about 3.9 time steps here. So maybe even 3.8, since this doesn't cross completely on this. So I might call it about 3.8. So 3.8 times 3.8 times our relationship up here. Time is in seconds. 1 over 3.8 times our number of divisions. So 3.8, these are all 100 microsecond divisions. So 100 times 3.8 would be 380 microseconds. So it would be 0.38 of a second. So 1 divided by 0.38 of a second would be a little bit different frequency here. This is in hertz. This is in kilohertz right now. So what I'm in is a scale, so it's close to the same range of what we're working in now. So because this is starting from kilohertz, this is going to be on the same scale because of complex units. So 2631 and a half. So 2631 and a half instead of 2652 and a half because of the phase changes that are happening. So 2631 and a half. And we would want to do the same thing for the VT. For now, I'll just assume that these are slightly different in terms of their phase shift. So this is going to be phase shifted from this one. So it's going to be the same kind of frequency, and then it's going to be phase shifted by, we'll say it's phase shifted by, you get a value something like t over omega, so 2 pi over t, that same period. So 2 pi over t, and then our phase shift, this might only be with how that was shifting, it's about it looked to be about half of a single wave side of the wave. So it looked like it was something like 1. So I'm going to say that's phase shifted by somewhere on the order of maybe 90 degrees as my estimate. So a phase shift of 90 degrees, and it's very important to pay attention to whether you're using degrees or radians in the formula. Typically it's going to be radians, and so this is where being able to look at this, the phase shift is typically going to be in radians. So converting back from something like 90 degrees, we multiply by pi over 180, and so what we get is we get 90 over 180 is 1/2 pi is what our range is. So 1/2 pi, instead of calculating the actual number, I can say 0.5 times pi. So this gives us an approximate phase shift. And now we're going to do some fancy footwork where we're going to do the plotting. So that's going to include the range of, that's going to include our VS. So VS with respect to time. We're also going to do VC with respect to time. And we're going to do VT with respect to time. So what we will get then is all of our output is suppressed. We do have some kind of a title. Sure, call it untitled. I don't care. Give me the plot. I need the plot. Here we go. We will get getting interference with the controls here. I will get the 3 overlaid and time shifted. So it helps to have a legend on these. You can zoom in and out using the scroll wheel, get a sense of what's actually happening. We can even reduce the time a little bit and go to something like 2 or 3. So I'm going to wipe out that plot and let it redevelop the same figure. There we go. It's a little more clear. So what we can see is a plot, and it'll be easier to do time as X. So I'm going to flip those. It's as simple as doing this, because this is something that makes more sense logically to the way that we think. So presto changeo, and we get our much more recognizable plot back. Again, trying to show you guys a few MATLAB tricks along the way as far as how we set this up. And you can see that what we observe is the same kind of behavior. We see the overall input waveform, we see the lower output waveform, and we see the phase shifted waveform from one to the other. And you could refine these time steps to make them much more clear in terms of how that's done. So this looks a little bit more like what we observed on the graph, right? But you just want to be careful about how that gets plotted. So overarching theme is these allow for much larger overall scales of things. You can play around with a lot of variations of the timing in order to get the kind of figure that you want to see with the right level of detail. But again, you can see waveforms piggybacking on waveforms, and this is what some of that actually looks like. So what we're trying to do is get you guys to understand that these are different plots relative to each other, and then you can come back and do some more cleaning up and manipulating of the code for how to get a clean plot that's representative of what you're observing in your actual measurements.